Thank you, Amir. That was my next question. So here we go. So lecture 20. This is Friday, May 8th. The last of the two people, we are done. We made it to the finish line. And again, before I start today, I just want to say I'm going to do too much today. It will feel like too much. I want to do too much because as much as possible, I want this to be a repeat on Monday. So I want the weekend for you to digest all these things, and I want it to be a repeat on Monday. Okay? So having said that, here we go. So what have we been doing? We are saying, okay, infinite sum is this series, which in notation can be written as n equals 0 to infinity an or n equals 1 to infinity an. Whichever way you say it, it is an infinite sum. So this is for you computer science people, where your initial condition, that is what you say, is 0, a sub 0. So this is what a0, a1, a2, a3, infinitely many terms. What is this in notation? Oh, a1 plus a2 plus a3. So this is the first term and the second term and the third term. That makes sense ordinarily. What about this one? Or we will call this the initial term. So all of you computer science, computer engineering, you know that you always start with an initial condition and then you build upon it. Having said that, what were we saying? Oh, I can write one particular sum, which is this one, as a function. Not only that, I can tell you the radius of convergence, which is 1. I can tell you the interval of convergence, which is negative 1 to 1. So what are we saying? We are saying, and I want to emphasize this over and over and again. So look at the two sides. You are saying this infinite sum is equal to a function. And it is equal to a function for what? Only for values of x between negative 1 and 1. So the question yesterday was, can we write more functions? Is this the only function that we can write? And the answer is no. So can we write more functions as series? And the answer there was yes. And then how do we do it? And I'm going to remind you, we do the algebra. We integrate, which we saw yesterday. What we did not see is the differentiation. And I'm going to do that one today. So, okay, you've started with one function with a certain radius and an interval of convergence. And now you are doing something to it to write a new function as a series. So the question should be, what happens to these two? I'm just going to remind you that when you do algebra, really, we go for substitution. So in this series, and I'm always talking about this one. So in this series, when x is replaced by a times x, what the heck is a? Constant. Tell me what should be the interval of convergence. When x is replaced by x over a, what is the interval of convergence? So I just want these two things from you. I'm going to make that box a little bit bigger. And for integration, thank you, Cecily, negative a to a. And when x is replaced by x over a, and this is I, the interval of convergence. Very good. Negative 1 over a to 1 over a. Why is this important? Because after we've done the algebra, the theorem says, and I'm just going to call it theorem 2. I think it is Cauchy's theorem. I don't remember now. But theorem 2 says that you can integrate, I stands for integrate, and D, the series, term by term. Meaning just take the D of each term, just take the integral of each term. Then what do we? If you're doing integral, you better find C, the constant of integration. But then the question is, oh, what happens to the same thing, the radius and interval of convergence? So I'm just going to say, The radius stays the same. For the interval, check the ends. And with that, I'm going to take an example of differentiation. So how do you think about this? So here's my first example. So I want to write f of x equals x over 1 plus 4x squared as series. So when I give you this function, then you're thinking, okay, how to do it? Well, your tools are just this and this box. So your tools are these two boxes up there. So remember, you build the plan depending on the function. So I want you to completely pay attention, all of you, because this is so just pay attention right now. So you want to write this as a series. What do you know? You just know this. Okay, so I'm going to build a parallel. I'm going to build the plan here, which I like to call the plan. And the plan comes from the function. So when I talk about this plan, and I want, you can unmute yourself today, but I want this from all of you. If I start here, and these are my questions. So if I start here, can I write 1 over 1 plus 4x as a series? This is like a puzzle. So if I start here, do you think you should be able to do some algebra and write 1 plus 1 over 4x as a series? And the answer is, thank you. And let's work out the details later. Now I'm looking at this function. So tell me, if I integrate this function, what will I get? I don't want the exact answer. I just want the function I'll get. So if I integrate this one, what will I get? ln. Very good. But if I differentiate this one, now what will I get? And that's very interesting. So if I differentiate this one, and notice I'm writing this as 1 plus 4x to the negative 1. So when I differentiate this, don't I get in other words, don't I get negative 4 over 1 plus 4x squared? And that is what that one looks like, isn't it? So it seems like, so what is the plan? I'm going to start putting here. So use algebra and write this as 1 over 1 plus 4x as a series. Then what? Then differentiate. Because when I differentiate, I get this. And I will get a series here. How do I know? Because it says differentiate term by term. And I'm going to work this very, very carefully. And now you can start writing with me. But I want this. I don't want this. So I will get to cross that bridge when we get there. Ready for this one then. So here is the plan. So here it is. So we will start with x to the n equals 0 to infinity, 1 over 1 minus x. So I'm going to remind you that I want to write 1 plus 4x as a series. So I'm just going to do a series of steps, which is pun intended there, which means here, and see if you agree with me. So first thing, I'm going to replace this x by negative x. Of course, I do it both sides. So now I'm going to get negative x to the n equals 0 to infinity, 1 over 1 plus x. Agreed. And at this point, if you have any questions on any step, you're just going to unmute yourself and you're going to say it. I'll be okay there. So I'm just going to say this is the move. And we are building that function that they asked us to write as a series. So if I don't see any questions, I'm just going to assume you all are okay. And so here is my next move. I'm going to replace this x by 4x. So here we go. And before I do that, I'm just going to separate this, and I'm going to say this is negative 1 to the n, x to the n equals 0 to infinity. This is me just writing it, just making things clear. So if we are all right there, then here we go. Then I get n equals 0 to infinity, negative 1 to the n, 4x to the n over 1. So far, so good. So it has to be that clean. It's just substitution. You've done substitution. You know the technique of substitution. So this should not surprise you at all. Shall we okay now? Very good. And now, remember, I'm going to write, differentiate both sides. Maybe I should write this way. Maybe this will be nice. So I'm going to go back and I'm going to say, okay, I start here. And here is my first move. X by negative x both sides. Then my next move was, and I'm going to write here, x by 4x both sides. Is that better? Okay, thank you, Cecily. So I'm hoping that she's speaking for all of you. Thank you, Trent. So here we go. So now I differentiate both sides. And remember, I do it very calmly. I do it side by side. This function, I know how to differentiate. In fact, I already differentiated that up there. So I know I get negative 4 over 1 plus 4x squared. I know my derivatives. So now I come back here. And here, just to make things clear, I'm going to write this out. So what was this series? So here we go. What am I trying to do? I'm trying to write this series. So can I write it out first? So I'm going to move this down here. So first I'm going to write it out. And I'm doing this for a reason, and you will see where. So don't write anything. Just follow with me. So this is what? Negative 1 to the 0, 4x to the 0, plus negative 1 to the 1, 4x to the 1, plus negative. See, this is where I missed that whiteboard now. I wanted that whiteboard in the classroom. I assure you I would have filled every corner of it. In fact, in our class, I would have used all the 6 boards, all the 8 boards. We had 8, right? 3 front, 3 back, 2 sides. Right, people? Oh, visualize that beautiful room. But anyway, so thank you, Joshua. So here we go. So this is going to be 1. Minus 4x plus 4 squared x squared minus 4 cube x cubed. So these are the terms, and they are equal to 1 over 1 plus 4x. Why am I writing it out? Because this is the first example you're seeing. After that, yes, trickery. We are not going to write it out every single time like that. So if you're wondering, oh, am I supposed to write this out? No. But the first time, yes, because you have to see it. Now I'm going to differentiate both sides. So when I differentiate both sides, what do I mean? Oh, I differentiate the function, d of the function, which I know is negative 4 over 1 plus 4x squared. In fact, I decided to differentiate because you wanted that particular function there. And now all of you stop writing. And when you differentiate, so how do I differentiate this? Oh, we differentiate each term. We d each term. We d each term. We d each term. So tell me, what is the derivative of the first term? And you can unmute yourself if you want to say, so what is the derivative of the first term? What is the derivative of 0? 1, I gave the answer. Sorry. So derivative of 1 is 0. Derivative of this term, thank you. Derivative of the next one, can I say derivative of the next one, can I say so now if I have to write this in notation, what do I observe? Remember, what was this? Wasn't this n equals 0? Wasn't this n equals 1? Wasn't this n equals 2? Wasn't this n equals 3? Yeah, that was what it was. But when you take the derivative, what happens? Oh, you drop 1 down. Why? Because the derivative of the constant term just goes to be 0. So what do you have here? Oh, I have n equals 1, n equals 2, n equals 3. I just have those terms. So if I have to write them in series, I'm going to say a summation n equals 1 to infinity. Now let's take care of each bit, and that is why I don't want you to write. So I'm going to take care of each bit separately. And what do I mean by that? First, I'm going to look at just the exponents of 4. So it seems like you have 4 to the n. Then I'm going to look at the exponents of x. Oh, that looks like you have x to the n plus 1. Sorry, n minus 1. Because when n equals 2, x is 1, n equals 3, x is 2, and so on and so forth. And what do you have? These numbers seem to be n, the parentheses. And the series seems to be alternating. So tell me, this should be negative 1 to the what? Very good. And this is negative 4 over 1 plus 4x squared. And just because we don't have that board, I'm going to remind you, but f of x was x over 1 plus 4x squared. So tell me, how do I write this? I came till here. We came till here. Now what do I do? I want to get here. This is what I want, not this. So what do I do? So I'm going to say, first, let me divide or multiply both sides. So here is my next move. So I am going to multiply both sides by negative quarter. Why negative quarter? Because this will get rid of the 4. I did not want that 4 there. So here we go. So I'm going to say, so this is going to be negative 1 over 4 times negative 1 to the n, 4 to the n times x to the n minus 1 equals 1 over 1 plus 4x squared. So when you times this by negative 1, then I'm just going to say this was n equals 1 to infinity. So see if you agree with me. So I'm going to say this is n equals 1 to infinity. Negative 1 to the n plus 1, because you have there. 4 to the n minus 1, n x to the n minus 1 equals 1 over 1 plus 4x squared. So far, so good? So I'm just going to finish this problem and then take questions. But I wanted this, remember? There's x on the top. So my last move is I'm going to multiply both sides by x. And I have, I'm going to take one more example, do not worry. So this is going to be negative n equals 1 to infinity, negative 1 to the n plus 1, 4 to the n minus 1, n x to the n minus 1 times x equals x over 1 plus 4x squared. And that's it. That's the series. Why am I not combining this yet? For a reason. Because I want to go back and do something. And for that, I need your complete attention. So I want to go over this problem over one more time. So ready. I don't want you writing at all right now. Ready for this one? So I want a yes. I want some kind of indication from each and every one of you. So you should not be writing at all. You should just be watching this. So let's go back to the beginning of the story. So what was this? Oh, you said you wanted to write this as a series. That was where the game began. So then you came up with a plan. You said, okay, if I start with this, then I can do some algebra moves and write 1 over 1 plus 4x as a series. Once you are done that, then you said, okay, if I integrate this, this is going to give me ln. So I can't integrate this. That means, what am I left to do? Differentiate. So will differentiate give me that square at the bottom? Yes. So I was okay. And so I started. So I started building off this series. First, we replace this x by negative x. I like to do this. So if you want to take shortcuts later on, you can take a shortcut. And I'm going to tell you what that shortcut is. So I replaced this x by negative x. I came here. Then instead of x, I put 4x and I got this. So I got the first part of the plan, which was algebra. That was done. Then what did we do? Then we agreed we're going to differentiate. So we differentiated both sides, but the function differentiation, I know, this is my Calc 1 class. How do I differentiate the series? That is my Calculus 2 class. We differentiate each term, and so those were the arrays. So when you differentiated this, I want you to understand, look, this was your series, wasn't it? This one. Look at what you ended up with, and that's why I didn't erase that. Look at what you ended up with. You ended up with this one, which means what? You just differentiate the x to the n term, isn't it? And that is what we do in derivatives. If I ask you the derivative of 3x squared, it is 6x. In other words, it is, and I'm going to erase that, and I'm going to say, isn't it 3 times 2 times x? And that is what I'm getting at. That this constant, you can sort of throw aside, move it aside, and you're saying it's just the differentiation of this one. And so if you notice that if I write here 4 to the n x to the n, then where you came here is your constant is the constant, and your x to the n, you just use the formula for derivatives, because each x to the n is n times x to the n minus 1. And that's the shortcut I want you to take. So why did I write this in between? Because I wanted to show you that when we differentiate, you differentiate it term by term. The other reason I did it, because you have to understand when you differentiate, you drop one down. So your series does not begin at 0 anymore. It starts at 1 because it shifts 1 up, because you lose a term, you lose a man. And so you do this, and then you just manipulate the way you want to. I'm going to finish my time by saying this, that the idea was, oh, what about the radius of this convergence? So I'm just going to say this to you. What was the move you did? You did x replaced by 4x. When you did this move, what happened to the radius? So x was replaced by 4x. I'm going to go way up there to my box. Oh, x was replaced by 4x. So what happened to that move? What happened to that radius? It went from what? So I'm going to say negative 4 to the 4. And Now I'm going to go back and question this. And I'm going to say, okay, if I replace x by ax, then what happens? It is ax less than 1, isn't it? So isn't this kind of switched? Do you have any idea what I'm talking about? So shouldn't this be, and we are going to correct ourselves. So this is what? Negative 1 over a to 1 over a? And when you do this, this is negative a to a. And I'm going to prove with another example, so don't worry. Tell me, people, are we okay? This is the first time you're seeing it, so that is why I wanted to do this today. And I'm going to do another thing today, because Monday we get to repeat. Monday I'm going to pick examples and I'm just going to do this. No, Cecily, you're fine. That is how we learn. Because every time you can't be referring to notes, and this is what I was trying to say to you, that every time, even though you might have your notes on there, if you spend too much time just ruffling through the notes, you will not be able to finish the final. And so we just are going to go with that. So Jiva, for you, here is the next example. So you're going to look at this in your own sort of way, but I'm going to start with the next example. And here it goes. So this time, what do I want to do? And let me start with, so I took a little bit heavy example for a reason, which is what I wanted to do. But now let's do with this one. So I want to write f of x equals x over 2 minus x squared as a series. So, where do we start? We always start with this one. So, here we go. And we have to understand what we're doing. So I'm going to say, can I write 1 over 2 minus x as a series? And this is a question for all of you. And unmute yourself and start telling this to me. Yes or no? Can we write this as a series? Starting here, meaning what? When I say starting here, you have to remember you have 3 tools with you. You can use A, which is algebra. You can differentiate. You can integrate. So if I have to write this as a series starting from here, which tool am I picking? A, D, or I? Very good. So we are picking algebra. So when you're picking algebra, how are we doing it? So here, I'm going to remind you, we're going to do what? So we are picking A. We will factor out the 2. And I will write this as 2, 1 minus x over 2. Why am I writing it this way? Because then I'm just going to replace this x with x over 2. And I'm just going to multiply by half. Done. So, okay, algebra done. So I wrote this as a series. So tell me, to get this, so here we are. So we are going to assume, yes, A done. We wrote 1 over 1 minus 2x as a series. So this is equal to some series. We'll fill in the blanks later. So tell me, now what do we have? We have 2 other tools, right? Differentiation, integration. So tell me, when I integrate this, what function do I get? So if I integrate 1 over 2 minus x, very good, I get ln. But I do not want ln. This is not what ln is. So I'm going to say, okay, integration is gone. It doesn't work. That means I pick differentiation. So I'm going to take the derivative of this one and I'm going to keep it ready. So when I take the derivative, what do I get? I claim I get -1, 2 minus x squared times -1. In other words, I get 1 over 2 minus x squared. Oh, close. That's what I wanted. And that's it. That's where I began. So now I start. It is time to execute the plan. And so here we go. So we start. And this is the one I'm going to work carefully. Just like that. But it's going to look a little bit more cleaner than the other one. So what was the thing? Oh, I'm going to replace x. So here we go. X by x over 2. And at this point, I'm going to say, okay, if I'm going to replace this x by x over 2, what happens to the radius? So what happens to the radius there? Or rather the interval? What happens to the interval there? Very good, Trent. So interval will be -2 to 2. This is a path series centered at 0. We know that. So radius is just going to be 2. And I'm going to keep that ready. And so here we go. So summation n equals 0 to infinity. Sorry, I mean to change the color because I want to keep this very much color coded. So this is going to be n equals 0 to infinity. X over 2 to the n is 1 over 1 minus x over 2 because that's the only move you did. But remember, when you factored out the 2, now you have to multiply both sides by half, isn't it? That is because that was up there. So here we go. So I'm going to multiply both sides by half. And I'm going to write this as where did this come from? I'm just going to remind you, this was x to the n over 2 to the n. You multiplied by half, so the exponent of 2 just went up. And I'm going to remind myself, oh, the radius is 2. Because I haven't done any substitution or anything like that, so I'm going to carry that radius with me. Now what? Oh, now I'm going to differentiate both sides. I already know the derivative of this one. I kept it ready over here. So I'm going to say, okay, I know the derivative. The derivative was going to be 1 over 2 minus x squared. How do I do the derivative here? Oh, I ignore the constants. So I will go, this is just taking the derivative of this one, because this one is just a constant. So I'm going to say this is n, sorry. Just like that. Because you can say, I'm going to push this aside, 1 over 2, and just take the derivative of this one. So what am I missing? I took the derivative, isn't it? So this should be n equals 1, because we are 1 man down. Because the first one, which is x to the 0, which is a constant term, is going to be, the derivative of that one is going to be 0. I'm reminding myself the radius is 2. Oh, the theorem tells me if even after you differentiate, the radius still stays at 2. I'm going to go back up and say, is this the function I needed? No, I needed x over, so I'm going to multiply both sides by x. There you go, Joshua. So to finish this, multiply both sides by x. And you're saying, therefore, this is n equals 1 to infinity. n x to the n over 2 to the n plus 1 over x over 2 minus x squared. When is this true? Oh, radius is 2. That means as you put numbers between -2 and 2, we are okay. What about the ends? I really don't know about the ends, so I'm just going to write it in words. Oh, any number between -2 and 2, because I don't know about 2 and 2 themselves. So this is true for any x between -2 and 2. Are we okay there? So the question should be, why are we doing this? So are we okay there? So I'm going to pause a little bit. Maybe you're writing and I want questions here. So I'm going to pause, take questions, because I'm going to go to the next idea. We put that, Joshua, because here is what I'm pointing to you, if you can look. So this was 2 to the n, correct? You are multiplying each term by half. And so what happens? Your 2 to the n times 2 is 2 to the n plus 1. Because remember, when you're multiplying by half, you have to understand that this is infinite terms. You're multiplying each one of them by half. So everybody's denominators goes up. The exponent of 2 rather goes up. Did I answer your question, Joshua? Okay. Jivu, I don't understand the question. What do you mean, wouldn't it be -1? Which one are you talking about? Okay, Jivu just gave up on me. Oh, Cecily, maybe you understood her question. Okay. So are we okay there? So now for some trickery. So here are some tricks. So here is what I'm going to remember. And I'm going to put it in boxes. So I'm going to remember that sigma x to the n equals 0 to infinity. Hey, notes or not, I'm going to remember this, is 1 over 1 minus x. I'm going to remember, oh, this is a power series that is centered at 0. Its radius is 1, and its interval of convergence is -1 to 1. Well, the counterpart, I'm going to remember that summation n equals 0 to infinity -1 to the n x to the n is 1 over 1 plus x. It is a power with the same radius as 1, and interval is -1 to 1. Why is that? Don't we go from here to here when we replace x by -x? But then it is still a geometric series, isn't it? And for geometric series, what do you say? You say absolute value of -x has to be less than 1. Well, absolute value of -x is still x. And so they are the same. And so I would remember just these two. So what is the shortcut then? Remember, I asked you to write whatever that was. What was that function? X over 1 plus 4x squared. So I might just start here. And I might not start here. If I ask you to write x over 1 minus 2x squared, I will start here. And then you sort of know what to do. Are we okay? I want to build this story today. And I told you I'm going to build this story because, again, repeating myself, on Monday, I'm going to do the same thing that I do today. I don't want to start any new thing on Monday. So the story continues. What is the story right now? I do understand that you will need to take a look at this little more, look at the homework, and only then it is going to sink in. That is why I'm going to do it today, so that you have the weekend and Monday you're just ready with questions. Today, if you have time, you want to stay behind, and we will work some more. That doesn't mean I'm on Monday. We will stay behind if you want. We'll do more, and we'll figure it out. But let's go on and do this. So here is the story so far. So, okay, I start with these two, and I seem to do what? ADI, and write other functions as series. But this is still limited. So I'm limited. I can't write all functions as series because, I can only do what to this? ADI, which is what? Differentiate or integrate. If I integrate any of the functions that look like this with the only thing I get is ln. Oh, but surprise, surprise. I can use this to write 1 over 1 plus x squared as series. I integrate this one and I get tan inverse x. Oh, not bad. And now I'm wondering, okay, so what about the other trigonometric functions then? So what about, why can't I write e to the x? Because, if I integrate, I can write ln. So what about the inverse of that one? Why can't I write e to the x? What about sine x? What about cosine x? There are so many functions I know. What about hyperbolic cosine? I'm not scaring you. We're not going to go there. What about sine inverse x? We can't do that. We don't have time. But if we had, which I did last semester, we would have done sine inverse x as a series. And that goes to your question, Sadhana, which you asked last time, that is there more ways to write pi as a series? And the answer was yes. If you could write sine inverse x as a series, then, sine inverse of 1 over square root of 2 is pi over 4. And there goes the game. So, Sadhana, did you hear me? Is she here? So I don't know if Sadhana is here, but that was the question she posed last time. But anyway, so we are not going to get that, but it's not going to stop us from writing these things as a series. Okay. And for that, completely stop writing. Just watch this mumbo jumbo, because I like to do the mumbo jumbo with you. And then we are going to do a very simple example. So here was the idea. Here's what I'm motivated. That I can write tan inverse as a series. I can write ln of something as a series. Why not the others? So I'm going to assume a big if, literally a big if. So if I assume that I can write any function on this earth, you give me a function, any f of x, as a power series. It might be centered at A, or it might be centered at 0. Hey, if it's centered at A, it looks like this. If it is centered at 0, it looks like this. If it is centered at 0, it's called a Maclaurin series. If it is centered at A, it's called a Taylor series. So this is the big if. If I assume, notice what am I saying? I'm saying I pick any function on Earth, and I can write this as, and I'm starting with Taylor's, I can write this as C sub 0, again, do not write this, plus C1 x minus A to the 1 plus C2 x minus A squared, and so on and so forth. And listen to me very carefully. So what do we know here? This, because I picked the function, I wanted to write this as a series. I know A because I picked it, so I picked it. So I know this. So what is the one thing I do not know? I do not know the C's. So I know the function, I know A, I just do not know the C's. So the idea is, oh, so if I somehow figure out the C's, if I can find the C's, the C sub 0, C1, C2, C3, then that's it, I'm done. And so I want all of you to participate now. So tell me, this is the function, you know f of x. If I want to find C0, if I want to find this one, what value of x should I put in here such that everybody vanishes and just C0 remains? Who would that be? Very good, Cecily. And I'm going to take Cecily's suggestion. I'm going to put A both sides. So if I do that, x equals A both sides. Do not write, just watch this. So what do I get? F at A is C0. Not bad. C0 is f at A. Okay. Now what am I going to do? I'm going to differentiate this. Why? Because I just found out if I differentiate, I go one term down. So I'm going to differentiate. I'm going to name this. I'm going to differentiate this, number 1. So when I differentiate, what do I get? F prime x is C1 x minus A plus 2 C2 x minus A. Sorry, I shouldn't get this, so I just get C1. Sorry, I'm going to write this carefully. Again, I missed the board. Plus 2 C2 x minus A. Hey, if you're wondering, then I'm just going to say this to you. C1x minus A is what? C1x minus C1A. So this is a constant, so the derivative is 0. And the derivative of this one is just going to be C1. That's why I said do not write. And I'll be okay there. Are you with me? Because it's easy to get lost. If you're writing, you're lost. If you're not writing, then you're with me. And I'm going to write one more term here. So this was what? C3x minus A cubed. So I'm going to say this is 3C3 x minus A squared, and so on. So tell me, to find C1, what value of x should I put in? So what should x be? So that I will get the value of C1. And that value should be, meaning everything else disappears. C1 just remains. And that would be, so remember here, all these should disappear. All of these should go away. Only this guy should remain. So what value works then? Yes, Cecily, it is A again. We found something, so we keep repeating. Why reinvent? So if I put x equals A, then I get C1 is F prime A. Okay. I'm going to call this 2. And it's laundry time now. Rinse and repeat, which means what? Oh, I'm going to differentiate 2 now. So what do I get? Oh, I get F double prime x equals 2C2 plus 3 times 2 times C3 x minus A plus something. I don't have space to write, so I'm going to stop there again. So here is the question to you. What value should I plug in here? X should be what? So that C2 remains and everything else disappears. And that's going to be and I hope you're not writing, and that's going to be x equals A again. So it will be x equals A both sides, and I get C2 is F double prime x over 2. And now I'm starting to see a pattern. And what pattern is that? And I'm going to write it for you. So C naught was f at A, which means what? It was the value of f at the center. C1 was f prime at A. It was the first derivative at the center. C2 is f double prime, A over 2. Oh, it is the value of the center, but you've got a denominator now. So I'm just going to interest you in seeing this. So can I say this is fa over 0 factorial? C1 is f prime a over 1 factorial. C2 is f double prime a over 2 factorial. So I have found a formula, people, that Cn is fn at a over n factorial. Yeah, if I have to write it in words, I'm going to say this is the nth derivative at the center over n factorial. And it gives me what? It gives me Cn. What do I mean by that? Oh, I just mean when n equals 0, it gives me C sub 0. When n equals 1, it gives me C1. When n equals 2, it gives me C2. When n equals 25, it gives me C25. Let's put this into action then. So here is the example. And so I'm going to write it. So here we go. And this is what it is on the cheat sheet that I gave you. So I'm going to start from there. If f of x is to be written as a series, let's say it is to be written as Maclaurin series, which means you're writing it as Cn x to the n goes from 0 to infinity. Then how do I find the Cn? A Cn is the nth derivative at the center over n factorial. That's the formula. I like to work this in a table, so I think the example will make it clear. So here's an example. Example that I wrote up there. So I want to write f of x equals e to the x as Maclaurin series. So I'm going to start with this. So here's the solution. So I want to write e to the x is summation n equals 0 to infinity Cn x to the n. I just want to find those Cn's. So what do I do now? For me, I make a table. So here we go. And I'm going to remind you what is Cn in words. So Cn is the nth derivative of f at 0 over n factorial. So I'm going to start with n. Derivative. The derivative at the center, so I'm saying fn at a, and then the coefficients. I've picked a very simple example just because I want to do 2 of them. And I want your participation now. So I want somebody to unmute themselves and answer the questions if you can. So I want one spokesperson. So it could be Trent, Joshua, Sadhna, Aaron, Almari, anybody, or a couple of you together. So here we start. Your n starts at 0, so I'm going to start at 0. So if n is 0, are we taking any derivative? It's the nth derivative of f. So if n is 0, are you taking any derivative? Very good. So what would the function be? Just e to the x, because remember, this is your f of x. Now what? You evaluate the derivative at the center, but your center was 0, so keep it at 0. So you're going what? E to the 0. So what is this coefficient? 1 over 0 factorial, which is 1. N equals 1. What does that mean? We are taking the nth derivative. If n is 1, we are taking the first derivative. Is there one person who can unmute themselves and talk to me? Because this is, I need somebody, I need that feedback. I can't be looking at that chat. So I understand some of you might be home and you cannot unmute yourself, but is there one person who can unmute? But don't give up now. Come on, last 2 days, you made it this far. So I think I'm going to call on my favorite person, Trent. You were supposed to be reading problems, remember?
I'm here.
Okay, Trent, here we go. So you are, I will help you there. So if n equals 1, Trent, that means what? We are taking the...
It's the derivative, right?
Right. So if it is the n equals 1 and you're talking about the nth derivative, then Trent, you must be taking the...
Let's see here. I was trying to catch up. I was kind of fell behind, but let's see here.
N equals 1 and nth derivative, that means you're taking the first derivative. So what is the first derivative of that function e to the x? It is still e to the x.
Right.
Very good. What is e to the x at your center 0, which is still e to the 0? And so what will the coefficient be? Look at this one. You need to divide by n factorial. So it is 1 over 1 factorial, which is 1. So I'm going to continue. So if n equals 2, now go Trent. If n equals 2, what derivative are you taking?
The second derivative.
Very good. The second derivative of who? The second derivative of the function. So what is the second derivative of the function?
Still e to the x.
Thank you, sir. This derivative evaluated at 0 is...
Is it still e to the 0?
Very good. And now what is the coefficient? 1 over 2 factorial. Because look at this formula up there. And so this is half. So we keep going, and I'm going to do some more. So if n equals 3, now we are taking what?
The third derivative.
Third derivative of who? Of
The function.
So it is going to be what?
E to the x.
E to the x again?
Yep.
You are going to have what? E to the 0. And this is going to be 1 over 3
factorial. Yeah.
Very good. Let's do one more. N equals 4. That means what? Fourth derivative. Fourth derivative of who? Of the function. So it is e to the x. Evaluated at the center. So it's e to the 0. So it's 1 over 4 factorial. And now let's write it. And now I'm going to have this here. Because this is your C sub 0. This is C1. This is C2. This is C3. This is C4. So when you're writing that series, so you're saying e to the x is C sub 0 x to the 0 plus C1 x to the 1 plus C2 x squared C3 x cubed plus C4 x to the 4 and so on and so forth. So I'm just going to bring it down here. I'm going to say, oh, e to the x is then 1 plus x plus 1 over 2 factorial x squared, 1 over 3 factorial x cubed, 1 over 4 factorial x to the 4, and so on and so forth. Which, in notation, would be summation n equals 0 to infinity. Remember, this is what I do with, this is what my table is for. So then I start writing, oh, this is x to the 0, this is x to the 1, this is x squared, and I just multiply. So I'm going to do one more example, which is brilliant because that's what I wanted to do today, is x to the n over n factorial. So you have written this as a series. So what about the radius and interval of convergence? I'm going to leave it to you. So you're going to use the ratio test to find the radius and the interval of convergence. And you will be surprised. If I have time, I'm going to come back and do this, but I want to do another example. So let's do one more. So this time, I want to write sine of x as Maclaurin series. So here we go. F of x equals sine of x as Maclaurin's series. So I start again. That means I have to write f of x n equals 0 to infinity cn x to the n. What are the cn's given by? Oh, it is the nth derivative at the center over n factorial. So I'm going to write it in words at all. This is the nth derivative of f at the center over n factorial. This is what cn's are given by. So, and I do understand that this series is C0, x0, C1, x1, but I'm going to make my table work for me. So here is the table that I start to make. So I go n, derivative of f, then I go derivative of f at the center, so this one at 0, because that is what our center is, and these are my cn's. And what do I know? Each number here is multiplied by x to n here. So let's start. So if n equals 0, remember the function is sine of x. So if n equals 0, are we taking any derivative, Trent?
No.
Very good. So the derivative of f, meaning we are not taking any derivative, it's the 0th derivative of f, which is just going to be sine x. Sine of x at 0, meaning sine of 0 is
0.
very good, sir. So sine of 0 is 0. Sorry, I'm just trying to get to my table. So c sub 0 is just 0. And remember, this is multiplied by what? This is multiplied by x to the 0. That's the tab I keep, and I just write my things from my table. So if n equals 1, now we are taking the derivative of who? Of this sine x. Which derivative? The first derivative. So derivative of sine x is going to be
Cosine x.
Cosine at 0 is
1.
So C1 is 1 over 1 factorial. Now we go to n equals 2. N equals 2 is the second derivative of sine x. So isn't it the derivative of cosine x then? Right?
Yeah.
And so derivative of cosine x will be?
Negative sine x.
This one evaluated 0 is going to be, so this one evaluated at 0 is going to be
0 again.
So C2 is 0. I'm going to do a couple more, and here we go. So I'm going to go with n equals 3. So I'm going to take the derivative of this one, which is going to be
Negative cosine x.
this one at 0 is going to be
-1.
And -1 over 3 factorial. So I'm going to go with 4. So derivative of this one is going to be
Sin x.
negative sin x,
Oh yeah.
right?
Or
No, you're right, sin x.
yeah.
So at 0, this is going to be 0, so this is 0. So we come to 5, n equals 5. Derivative of sin x is
Cosine x.
cosine at 0 is 1. So we have 1 over 5 factorial. I'm going to do 2 more. 6. Derivative of cosine x is negative sin x, 0 and 0. So I'm going to go to 7. Derivative of negative sin x is negative cosine x. So I get -1, and I get -1 over 7 factorial. So how do I use this? So what do I get here? C1 is multiplied by x to the 1. C3 is multiplied by x to the 3. In fact, this tells me this is x to the 5, and this is x to the 7. Why am I not writing the others? Because see, they're all zeros. So first thing I notice, it is just odd exponents. So I'm going to write this. So here we go. So you're saying sin x is 1 over 1 factorial x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5 minus 1 over 7 factorial x to the 7, and so on and so forth. So what is the first thing I observe here? Alternating series. And then I'm going to look up my own table, because this, I can write this as summation. Remember, it was n equals 1, so I'm going to start with maybe n equals 1, or I can even start with n equals 0. So I'm going to start with, so here we go, n equals 0 to infinity. Let's do that. And I'm just looking at this one. So what about x? Oh, they are all odd, so it is 2n plus 1. Notice that this is this factorial down here. So this is going to be 2n plus 1 factorial. So took care of that. The only thing I have to take care of is their alternating. So tell me this will be -1 to the what? And I'm going to show you, okay. And very good, Cecily. This will be -1 to the n. If I wanted to write n equals 1 to infinity, I could have done that. In that case, it becomes what? -1 to the n plus 1, x to the 2n minus 1 over 2n minus 1 factorial. In both cases, I want you to see that when I put n equals 0, I get x. When I put n equals 1, I get -1/3 x cubed. When I put n equals 2, I get 1 over 5 factorial. So 3 factorial, sorry. X to the 5, and so on and so forth. And the same thing here, but the same thing here with n equals 1, I get x. N equals 2, I get -1 over 3 factorial x cubed, and so on and so forth. And now I'm going to take your question. So this is the end of your course. So what is remaining? So let me be clear about this. So what is remaining? So on Monday, we're going to do the same thing, but we are going to write this as Taylor series. Meaning this is centered not at origin, at something else. This is centered at A. So we are just going to practice the last 2 sections on Monday, which is 11.9 and 11.10, which is Taylor-Maclaurin and the other part, which is writing functions as a series. So I do want to know, just because you wrote this, so there are many subtleties that we don't have time to cover. Just because you wrote this, it doesn't mean that it is true. There was another theorem, but we don't have time to take care of. So all I want you to do is use ratio test to find the radius and the interval of convergence. So we are going to practice this table on Monday again, but with tailored series. In the meantime, yes, I have assigned you homework, which I'm going to make it due Monday midnight. So Monday, be ready with questions, ask all sorts of questions. If we need, then we will meet again, maybe not on Tuesday or Wednesday. Let's talk about it on Monday, and we will finish this unit. So I don't want to go past. Today is a Friday, so take this in. I have given enough material to you to go over. But before you leave, if you have time and if you have questions, then go ahead and do ask. If you need to leave, then I'll see you Monday. But these are sort of my office hours now. No worries, so see you, Sam.